So this is Griffiths, Electrodynamics problem 4.16. We'll have three different shapes here. One's a sphere, one is a needle, and one is a thin wafer disc. And these are going to be cavities that we're hollowing out of a dielectric that already has built into it an electric displacement. So a polarization and an electric field as well. So, and of course, the polarization can be due to the electric field. So I guess before we start, I want to talk a little bit about polarization, just because I think it will make more sense when we actually get into the problem itself. So suppose we have some material. Let me just draw it like this real quick. And we apply an electric field E naught to it. All right, well, inside this material we have little tiny atoms or particles that are polarizable. So that means, excuse me, that means that if we look at each one, you'll get a tiny dipole formed. So you'll get a tiny bit of negative charge on one side and a tiny positive charge on the other. And a really good way that Griffiths talks about this is like if you stack a bunch of these next to each other, so imagine a bunch of these side by side, you'll get a minus and a plus and a minus and a plus and a minus and a plus and a minus and a plus, right, all the way down the line. Okay, and if you look at these charges in here, these will tend to cancel out. So in essence, what you're doing, this is equivalent to just having the leftover charges, a minus on this side and a plus on this side. So that's what we're going to do, because imagine what we're doing is cutting a piece out of this dielectric right here. All right, well then, say we were looking at these charges right here, and before we had this plus sign here canceling with this minus sign right here. But now if we take out this plus sign and this minus sign and this plus sign and this minus sign, what's left over is a minus sign right here and a plus sign right there. So what this is equivalent to doing is we're adding in, suppose we had two pieces of dielectric. So if we look at this original piece here, we had a leftover charge here and a leftover charge here. If taking out this piece here is the same as superimposing a piece onto this with the opposite polarization. You see the plus signs and the minus signs, right? They all match up. So anyway, I think that will help make more sense of what we're doing here. So first we're looking at a sphere, and it is actually a spherical cavity. So if I color the background, this tells us it is embedded in some dielectric. All right, so I'm just going to say the outside the sphere, the electric field is this, E naught, and the polarization is also going in that direction. Which tells us, like, if we were to zoom out onto the very edges of the dielectric somewhere far away from the sphere, we would have a line of minus charges on one side and a line of plus charges. These are bound charges, right? Over here on the other side, and this is just the same as if we have these little slices that we talked about. Imagine a whole bunch of them right here. So this is just a series of those little slices. Now if we cut out this cavity, it's like superimposing something with the opposite polarization. All right, so we have this polarization, which would be there if we didn't cut out the cavity. I'll just write that as P naught. And then we have an opposing polarization that we're putting in there to cancel it out completely. And so what this is equivalent to is having, basically what we end up with is just a bunch of the opposite charge right here, bound charge, right? Remember when we took this piece out, there was nothing left to cancel this minus sign right here. So now there's an extra minus sign stuck on this side and an extra plus sign stuck on this side. So we get the minus and the plus. Okay, so for a sphere, for the case of a sphere, Griffiths has already worked this out for us. You can look at equation 4.14, and he tells us that for a sphere, so this is just looking at a uniformly polarized sphere and just says what electric field exists on the inside of that sphere due to the polarization. Meaning, you see, so looking at this sphere, like if we were to ignore the dielectric outside and look at just a polarized sphere, the polarization P is pointing from the minus to the plus, but the electric field goes from positive charges to minus charges, right? So it's actually opposite in direction to the polarization. But there is a factor of 3. And then we have our permittivity of free space here as well. Okay, so this is the electric field due to a uniformly polarized sphere. So now, remember what we wanted to do was insert a sphere with the opposite polarization and see what that did to the electric field. So we need the polarization of the cavity to be equal and opposite to the polarization of the material that was there. So that just tells us that this polarization of the sphere, which is also in this equation here, is actually minus the polarization which is in the dielectric surrounding the cavity. So now if we want to know the electric field inside this cavity, which, okay, remember this is the actual question that Griffiths is asking. Well, the first one, first we'll find the electric field, then the electric displacement. It is the original field that was there, plus the field due to this uniformly polarized sphere with the polarization opposite to the polarization out here. So if we look at what that is, let's see. So we have, here's the original polarization, and the sphere is opposite to that, and then the electric field is opposite to that polarization. Basically, we get rid of our minus sign. So what we have is if we're putting it in terms of the original polarization, we just have this polarization divided by 3 epsilon naught. Let me make sure I'm explaining this properly. Maybe I can write an intermediate step here. So what we wanted was this original plus E sphere. All right, so this is this term right here plus the electric field of the sphere. All right, and so I could have written this as E naught minus the polarization of the sphere over 3 epsilon naught. But then we know the polarization of the sphere is just minus the polarization outside. So that's why this turned into a plus. So, and does this make sense physically? Well, we see here that the electric field inside the cavity is actually larger by this polarization over 3 epsilon naught term. And that does make sense because if you look at the new bound charges that show up right here on the edge in order to cancel out the polarization, these bound charges would cause a field, a uniform field, right, that goes from the positive charges to the negative charges, which is in the same direction as this E naught field that was there to begin with. So anyway, so this formula right here does make sense. If we now look at D, first let's write out D naught. All right, so D naught, this is given straight in the problem, right? Equal to epsilon E naught. Okay, and then plus this polarization. All right. Well, now we know what the new E is. So if I write let's call this D of the cavity. Again, this is, so we found E of the cavity, now D of the cavity. And that is equal to epsilon naught times E of the cavity, what we found right here, plus the polarization of the cavity, which, again, the polarization of the cavity, this piece right here is equal to the polarization of this sphere that we put in there, plus the original polarization, which are equal and opposite to each other, right? So the polarization of the cavity is equal to 0, which makes sense, right? It's a cavity, it doesn't have polarization. So, so this term is 0. Now when we put in, we're just going to plug in this E of the cavity that we found already. So we have our permittivity-free space right here, and then we have E naught plus the original P from the problem, right, over 3 epsilon naught. Okay, so we're now in terms of the original variables that Griffiths gave to us in the problem. We could put this in terms of D naught as well. So what would that be? Well, that would just be equal to D naught, right, which is this, and then what we have left is a minus 2/3 of P. Okay. So let's see. Yeah, so that about covers it for the first part of this problem. Okay, so for the second part of this problem, again we have our polarization out here and our electric field out here in the dielectric, and this is a long needle-shaped cavity that has been carved out of this dielectric. So like we talked about before, if you zoom way out to the edges of this dielectric, you could you could find some minus bound charges out on this side and plus bound charges out on this side, because these are in response to this electric field here. And when we chop out this dielectric, just like we talked about in the beginning, right here, there's a plus charge right here that does not get canceled out, and a minus charge right here that does not get canceled out. So, but the reason that we are looking at this long needle-like cavity is because if we look, here in the middle of this long needle-like cavity, these charges are very small and far away compared to, where we're at. So, I don't know. It's kind of a contrived problem, but the point of it is that these charges don't actually add or take away much. They don't actually change the, I guess it would be adding in this case, but they don't add much to the electric field. It's just a very small correction. So the E inside the cavity is about the same as the original electric field. All right, so this is the first part of the problem. What is the electric field inside this cavity? The second part, if we go ahead and write our original electric displacement out here, right? I guess I could draw this along with these guys. So what is the D inside the cavity? Well, the polarization inside the cavity is 0 again, and we already found this E, right, which is about the same. Let me write this out. So epsilon naught multiplied by the electric field inside the cavity plus the polarization of the cavity. All right, but polarization inside the cavity is 0. So this is just E naught times the electric field inside the cavity, which we already claimed was about equal to this, the field outside the cavity. I'll go ahead and keep the little approximately equal sign there. Okay, and so if we put this in terms of the original D naught, this, subtract P from both sides. And there we have it. So here's the electric displacement inside the cavity. Okay, so now we come to our final example, which is a thin wafer-like disc, and very thin relative to the size of the dielectric and all of that. We have our same old dielectric. So out here we have an electric field. We've got our polarization out here and our displacement. All right, so again, this is just a long line of those, or a long series of those lines of polarization that we talked about. And when we cut out the middle piece, we no longer have a positive to cancel out this negative. So what we end up with are a series of minus bound charges and a series of plus bound charges on this side. And what does this look like if we're looking right here in the center, this looks like a capacitor. So we do need to find out, in order to get the electric field of a capacitor, if you'll remember, you use the Gaussian surfaces and everything, and you find out that the outsides cancel out, and the inside, the electric field, how should I call this? Electric field capacitor, CAP, whatever, is equal to just sigma over epsilon naught. Let me not write this as a vector, just as a magnitude. We'll get our directions just from the picture. So if we want to find the electric field of the cavity, right, what we're looking for, right, it was the electric field outside plus the electric field due to when we superimpose an object, in this case the wafer, with opposite polarization. What is the electric field resulting from that? And the electric field, you can tell by the charges, just like in the case of the sphere, right? The electric field is going to, of a capacitor, will get a little boost to the electric field. All right. Now, unlike the case of the needle, now the charges are very close and wide, and so the electric field doesn't, the contribution from this doesn't go to zero. All right. So the cavity here, right? The electric field in the cavity is this external electric field plus the electric field due to this sort of capacitor that we are throwing in here, right? And what is the charge on this capacitor? What is sigma? Well, it's just enough to cancel out the polarization outside. We can look at the sigma bound, the bound charge, surface density, and we see that we can get that from polarization dotted into the surface vector. All right. And we'll just figure out the direction of the vectors based on the signs of the charges and things. So, but the point of this is the magnitude of this is, if I do the magnitude is just P. All right, and so we'll have a sigma bound equals positive P on this side and a minus P on that side. So our sigma here is just P, which means we can write this out, E naught plus P over epsilon naught. Let's just be careful that we don't have a minus sign going on here, right? When we make this a vector. Is this contribution to the electric field in the original direction of the polarization outside? Just like we already talked about, it is, right? So here's our E cap. All right, it's in the same direction. All right, so this is a plus sign, and we can go ahead and make that a vector. So this is the electric field of the cavity. All right, this is one of the things that Griffiths asked us to find. All right, the other one was the electric displacement of the cavity. All right. If we go back to our original, let me write this for the third time. Going back to this. Now we have to find the the displacement of the cavity, which is just equal to permittivity of free space plus, or multiplied by the electric field of the cavity. Okay, remember the polarization inside the cavity is 0. We've canceled that out with these bound charges. The reason I write this up here is because we're going to put this in terms of D naught, just like we did with the other two. So plugging in our E cavity, right, we're just taking this and plugging it in here. We get a permittivity of free space multiplied by epsilon naught plus this permittivity of free space multiplied by the polarization over the permittivity of free space, which just gives us the polarization. And lo and behold, this is the very definition of our original electric displacement. So we see that in this case, the electric displacement of the cavity is actually just equal to the electric displacement outside. So there's the last piece of this problem.